So let's look at this question over here. So a rectangle measuring 30 cm by 40 cm is located inside a region of a spatially uniform magnetic field. Spatially uniform magnetic field means by every point in space, that's why spatially uniform. Every point in space, the magnitude and the direction of the magnetic field is uniform, is constant. So they tell you that this magnetic field here has a magnitude of 1.25 Tesla. That's the magnetic field strength. This field is perpendicular to the plane of the coil. So this is the coil, and this our page here technically represent the plane of the coil, because the coil is now on the plane of the page or the screen that you are seeing right now. Okay, so in this diagram, they show you that the magnetic field is pointing into the page. Okay, so the coil is pulled out at a steady rate of 2 cm per second, traveling perpendicular to the field lines. So they are going to pull out this coil out from this spatially uniform magnetic field, and it's pulling it out with a speed of 2 cm per second. So that means by this coil will move 2 cm to the right for every single second that has passed. Okay, the region of the field ends abruptly as shown as the region of the field ends at abruptly as shown. So you can see here they draw a dotted line here to represent that the magnetic field will end right at this point, right at this line over here. So if your coil pass through this line, then if your coil start to touch this line, then after that, some portion of the coil will experience magnetic field. Some portion of the coil will not have any magnetic field in it. Okay, so this is the point, this is the line that separates between having magnetic field and not having magnetic field. Okay, so find EMF induced in this coil when it is all inside the field, if it is partially inside the field, or if it's outside or outside the field. So right now you can see that the coil is all inside the field. You can see that you put your coil all inside the field, and as you travel with 0.0200 meter per second to the right, a portion of the journey, the whole coil will still remain inside the field. Means that even though you are moving to the right, but you are still staying inside the uniform magnetic field. But once you cross this certain line over here, then a portion of your coil will be in the magnetic field, a portion of your coil will be outside the magnetic field. So you see probably your magnetic field only covers like 70% of the area or like 30% of the area. That's partially inside the field. Then once you exit the field completely, you are all outside the field, then there is no magnetic field passing through the loop at that moment. So this journey here, at earlier phase of the journey, you will see the whole loop has magnetic field passing through it. And after some time, when you enter another phase, you see that only a portion of the area of the loop has magnetic field passing through it. And if you travel further, there's no magnetic field passing through the loop. That is the situation that we are given with, and they ask us to determine the EMF induced at these three different phases. So let's study the first phase first, all inside the field. So when it's all inside the field, that means that this loop here initially is somewhere near the left of the magnetic field region. Then you're moving to the right, and now it's leaning more towards the right of the magnetic field region. But throughout this journey over here, you can see that the whole area here is covered with magnetic field passing into the page. The whole area here is covered with magnetic field passing into the page. So technically, if you look at the situation before, you look at the situation after, both of them have the same area, is 0.3 times 0.4. Both of them experience the same magnetic field, which is 1.25 Tesla. Both of them share the same magnetic field, share the same area, and you're not rotating the coil, so you're not changing the angle. So your N, your B, your A, your cos theta, all of them are constant. So when you do your Faraday's law, you know that the magnetic flux linkage is equals to MBA cos theta. You know that for this situation, there's only one coil. They don't tell that there's how many turns. It's a one turn only. So in that case, your N will be equals to 1. Your B will be equals to 1.25. Your A will be equals to 0.400 times 0.300. And your theta will be changed to 0 degree. Okay, because you can pick, in this case, they define for you the magnetic field to be pointing into the page already. So the more appropriate area vector will be pointing into the page as well. So the angle between the magnetic field and the area vector is still 0 degree over here. Okay, so everything here can get a definite value, but that's not what we are concerned about. The issue is if you do change against time, you see that everything here can be pulled out from the bracket actually. Okay, for here I pull out MB and cos theta out from bracket, I leave A inside bracket. But as you can see, the area here, the whole area here is still experiencing the magnetic field passing through it. So there's no change in area that is experiencing the magnetic field. Therefore, this one will be 0. That's why after that, you take 0, multiply by anything, you get 0. That's why the induced EMF for this portion of the journey is 0 volt. In other words, when the coil here is moving to the right, but it's still staying inside the magnetic field, there will be no induced EMF produced in the coil. There will be no induced current flowing in the coil. That is when it's all inside the field. Okay, but if we proceed and study the situation where it's partly inside the field, then we can see that initially the whole area is experiencing the magnetic field, but as you progress to the right, you slowly get out from the region of the magnetic field, and at the end of the journey, the whole coil should be outside the magnetic field already. This is what happens in during a journey partially inside the field. Initially, all of the area inside the coil here experience magnetic field passing through it, but as you move to the right, slowly the area that is experiencing the magnetic field will decrease until at the end, there is no area within the coil that experience magnetic field passing through it. So this will be the initial situation. This will be the final situation. So the area initial will be the area that has magnetic field passing through it, and that's the whole area. So you can take 0.400 times 0.300 to get the area. But for the final area, you can see that there is no more area in the coil that experience magnetic field. That's the final situation when you end your partially inside the field phase. Okay, you end it when you are all outside the field. You will start it when you are going to exit the magnetic field. So this is the initial, this is the final. So your final, the width, okay, the width of the coil that is experiencing magnetic field is 0. Therefore, the A final will be 0. The length is still 0.400, but what is changing here is the width of the coil that is experiencing the magnetic field. You can see here the whole coil is experiencing it, therefore the whole width will be considered for our area. But when you exit fully, there's 0 width of the coil that is experiencing the magnetic field passing through it, so your width will become 0 for final. Therefore, your A final will be 0. Okay, so this is a change of area question. Even though you are moving the coil, you are not making the coil larger, you are not making the coil smaller, but this is essentially a change of area question because the area that is experiencing the magnetic field is decreasing here. Okay, it's not just the physical area that we are talking about. We are talking about the area that is experiencing a magnetic field, and in this case, the area experiencing the magnetic field is decreasing. Okay, so if we proceed to solve this question, how will we solve it? Well, it's again Faraday's law, negative d magnetic flux linkage over dt. So you can change the magnetic flux linkage to become AVA, NBA cos theta. For now, the number of turns will still remain as 1, so you can bring it out. The magnetic field we are not changing, it's still 1.25 Tesla all the way, so we can bring out the magnetic field. We are not making the magnetic field stronger, we are not making the magnetic field weaker with time. We are keeping the magnetic field as 1.25 Tesla. So you bring out the B. So the cos theta, you are not rotating the coil, you are not changing the orientation of the coil, so the cos theta can be bring up. So what's left in the differentiation bracket will be the area only. Okay. So the area over here, as I mentioned just now, can be represented by length times width. But as you can see over here, it's the width that is decreasing that causes the area experiencing the magnetic field to decrease. The length is still 0.400 meter, but it's the width that is staying inside the field that is decreasing. So therefore, when you change area to length times width, you bring out the length. You keep the width inside the differentiation bracket, because the length is constant, but the width that is inside the magnetic field is changing with time. Initially, there's 0.300 meter of width staying inside the magnetic field, but at the end, there's 0 meter of width that is staying inside the field. So it's the width that is changing. Okay, so now you have negative MBL cos theta with the width over the time. So if you think about it, how does the width decrease with time? It's decreasing with time using this speed over here, right? Because the coil here is moving out with a speed of 0.0200 meter. So for every second, it will move out by 0.02 meter. So every second, your width will decrease by 0.02 meter. So the rate of decrease of the width here is actually equivalent to the speed over here. But here I put on a negative because my width is decreasing. So I shouldn't put in a positive speed. I should add a negative in front of it because the width is decreasing. So negative is because the motion is causing the area to decrease. Therefore, it's causing the width to decrease. Therefore, this value here must be negative. Okay. Just a dB/dt. dB/dt, if it's increasing magnetic field, it's a positive dB/dt. If it's decreasing magnetic field, it's negative value for dB/dt. So if your width here is decreasing, so it's negative value. So the speed here, we know it's a magnitude. So we add on the negative to indicate that it's causing the width to decrease. So now we have everything sorted out. Then we can do our substitution. N equals to 1, B equals to 1.25, length equals to 0.400. The theta here is the angle between the magnetic field and the area vector. So the area vector is again still pointing into the page, and the magnetic field is also pointing into the page. So both of them are 0 degrees of 0 degree. So the speed you can substitute in negative 0.0200. The negative is again because it caused the width to decrease. So if you calculate everything, now you get the answer to be positive 0.01 volt. And this positive 0.01 volt here is important because positive here, the sign is indicating direction because they state very clearly the magnetic field is pointing in what direction. They state very clearly whether the area is decreasing or increasing. So everything is stated clearly, therefore the sign is carrying a meaning. It's a positive sign, therefore if you want to determine the direction of the EMF, you can determine it using right-hand rule straight away. So this is my board. Again, this is my board like this. So the area vector is pointing into the page, as you can see in the screen over here. The area vector is pointing into the page. Therefore, if you turn your hand, it will be a clockwise turn. It will be a clockwise turn. So that means during the process of exiting the magnetic field, you will experience a induced EMF that is in this direction over here. Okay, the induced EMF is in this clockwise direction determined by your right hand rule. If you determine it to be a negative value, then you have to flip the direction from clockwise to anti-clockwise. But now this is a positive value, so it's clockwise. So this is your induced EMF, and because it's a closed loop, you should also experience induced current. So there will be current flowing clockwise in this loop over here. Okay, so that is what happened during the journey when it exits the magnetic field. Okay, so now let's continue to look at the journey when it's all outside the field. So all outside the field, the explanation should be quite straightforward. Well, you know that MBA cos theta, if you are all outside the magnetic field, the initial area that has magnetic field is 0. The final area that has magnetic field is also 0. So the change of area is initial 0, final 0. So there's no change in area. So this one is 0. Therefore, induced EMF will be 0. Okay, so something important to take precaution of during this portion of the journey, when you're moving inside the magnetic field, you have 0 volt of induced EMF. Okay, when you're all outside the magnetic field, you have 0 volt of EMF. But when you are partially inside, partially outside, then there is changing area. When there's changing area, the induced EMF is not equal to 0. So the whole motion here only has a small portion of time, a small duration of time where you can find EMF. Okay, the initial and the final, there will be no EMF, but for a small portion of the journey, you can find the EMF to be not equal to 0. Okay, Here I would like to bring out something that you learned from SPM. You probably learned that if you cut through the magnetic flux, okay, you learn the cutting of magnetic flux causes induced EMF, right? So in this case, you can see that the wire is indeed cutting through the magnetic flux. Okay, you probably say you probably ignore the up wire and the bottom wire, and you can say that the left wire and the right wire is cutting through the magnetic field. Okay, but if it's cutting through a magnetic field, if you analyze it one by one, you'll find that this portion is if it's all inside the magnetic field, how should I say it? In this situation here, even though it's cutting through the magnetic field, there is no induced EMF, because induced EMF is not because you cut through the magnetic field, it's because you have changed your magnetic flux. Only you can have induced EMF. So last time we keep on saying about cutting magnetic field, right? It's not exactly accurate. If you take a loop and cut through the magnetic field, you won't have any effect. If you take one piece of wire only to cut through the magnetic field, then you will get induced EMF. Okay, we'll discuss that in the example later. Okay, but it's not always true that if you cut through the magnetic field, then you get induced EMF. You have to look at the situation, see whether there is change in magnetic flux or not. That's the main point over here. Okay, so that's it for this question over here. This is a question on how do you change the area to change the magnetic flux. You change the area by bringing the area out from the magnetic field or bringing it into the magnetic field. In either way, you experience a change in the area that experience the magnetic field. That is the reason behind the change in magnetic flux that causes your induced EMF.